All right, and welcome back to my stream. Again, my name is Joey. I'm going to be your one class teacher for today. What we're going to do today is I'm going to actually do a bunch of chemistry questions. So I'm going to do in terms of what we're doing here as one class is where we're providing math and chemistry help for an online lessons for us to kind of answer your questions if you have in the secondary school level. And today specifically, I'm going to do a bunch of chemistry questions. So in particularly in the grade 11 and grade 12 chemistry, as well as university level chemistry as well. Again, my name is Joey. I'm currently a secondary school teacher, math and chemistry as well. Those are my specialized subjects. And here, one class, what we're doing is we're providing free online lessons and videos and tutorials for students to access at home despite the school closures. So what we're going to do is we're providing these online resources for free, and you can kind of tune in 7 days a week to our stream if you want to kind of walk with us in this journey of learning together. So that's what we're doing. So without further ado, let's get started. So what we're going to do today is we are going to look at like 10 chemistry questions, and we're going to kind of work through those problems together. So let's do that. So I have a problem here. So again, this question is asking. This is a grade 11. So this is a grade 11 question in the Ontario curriculum. And if you're coming, if you are tuning in from the States, this is going to be just a general chemistry question for you. So let's look at this. So it says, what is the molar mass of aluminum? So what is the molar mass of aluminum is our question, as our first question of the day. So let me write this down here. So let's see. So what is the molar mass of aluminum? And that's gonna be our question today. What is the molar mass of aluminum? So take a minute to think about that question, and then we'll answer it together. I'm going to also bring up a periodic table, so I'm going to do that first, periodic table for you. And then this might help in terms of answering these questions here. So what is the molar mass of aluminum? Take a moment to think about that question. So what is the molar mass of aluminum? And again, we're going to do 10 questions for today. So molar mass of aluminum. So when we're talking about molar mass, we're talking about this concept of stoichiometry, right? So remember, we know the relationship between mass, molar mass, and moles, right? So if you recall from grade 11 in our stoichiometry unit, you have moles, or N here, denoted by N. Moles equals mass over molar mass, right? So moles equals, this is mass in grams over molar mass, which is grams per mole, right? And obviously moles is in mole, right? So that's kind of our formula. Or do we need this formula for this equation? In this case, we don't need it, right? Because what it's asking us is it's asking simply what is the molar mass of aluminum. And we can actually look at our periodic table and we can answer this question, right? So if you look at aluminum here, we know that molar mass is basically the atomic mass of our element, right? So it says here, aluminum here says 26.982. So that's going to be our answer, 26.982, right? Our molar mass, big M, of aluminum, so I'm doing subscript AL here, equals 26.982 grams per mole, right? And what we can do is we can actually use this to solve for some stoichiometric problem, right? If I were to extend this problem further and say, oh, how many moles are in 1 gram of molar mass, what we can do is we can actually use this equation. I'll do this in blue because this is the end of the question here. It's only asking us what's the molar mass, but we can do moles equals mass over molar mass. And we're assuming 1 gram, so we can assume 1.00 grams of aluminum. Sorry, I don't know what that is. Of aluminum. We're going to divide that by the molar mass, which is 26.982 grams per mole, right? Grams per mole of aluminum, and we can divide that out. Let me get my calculator. So it's 1 divided by 26.982, which would give us a mole. So the moles of aluminum in 1 gram would be 0.0371 moles of aluminum, right? And we know how to use these stoichiometric problems to solve for a question here. So let's look at this problem. It says molar mass is measured as gram per mole. That's good. Molar mass of aluminum is 26.982 grams per mole of this should be aluminum here. I don't know why they wrote iron here. They gave us a little history lesson here. The very first table, it's a standardized atomic weight. It's also called atomic mass. Okay, that's cool. figure out atomic mass of a component. Aluminum's mass is that. Molar mass can be founded by the formula. So its molar mass is mass given by the chemical formula divided by the amount of substance per mole. So this is 26.92. Good. So this is a great solution. Great solution and analysis. Sweet. Okay. So that's good. That's good for number 1. So we are good for number 1. So basically what we have to do is we just look at the periodic table for a molar mass, right? And if we had to solve for mass from moles, we would simply use this formula here. Moles equals mass over molar mass. So standard stoichiometric problem for number 1. Oh, sorry. Let's do number 2. So this here says a solution was prepared by dissolving 24.40 potassium chloride KCl in 25 grams of water. Calculate the mass percentage of KCl. So let's do A first. This is A, right? So this is a 4-part question. So it says here, what is the mass percent? Mass percent of KCl. So it's asking what is the mass percent of KCl. So when we talk about mass percent, what we're doing is we're taking the percentage or the ratio of the solvent and the solute. So it says here, so I can say that the mass percent of KCl equals, it would be a mass, obviously, the mass of KCl divided by total mass, right? So this would be total mass would mean KCl and water, right? And then times 100%, right? That's their definition of a mass percent. So I'm going to give you a moment to think about this question as well. And what you're going to do is, if you're in the chat, again, wave hi, maybe say hello. And what we're going to do is we are going to answer this question together. So again, mass percent of potassium chloride in the solution, right? And we're saying the solution is the water, right? The water is our solution here. So in 225 grams of water, right? So in order for us to solve this, what we can do is we have the mass percent, which is what we're solving for. So this would equal mass of potassium chloride. We know it's in grams, right? So in grams, we have it's 24.0. So we don't have to do much math here. 24.0 KCl. And so we're going to divide that by the total mass, right? The total mass would be the mass of the total solution, right? So the total KCl and water, right? So this would be 225 grams of water plus 24, right? Plus 24.0 grams, right? And this would multiply by 100%. So this give me 24 grams over, this is 225 plus 24 would be 249 grams, I believe, times 100%. And then what I can do is I can simply just plug in my calculator, right? So 24 grams divided by 249 times 100 would give me a value of 9.64. 9.6. I have 3 decimal places, so this is 9.64% here. I'm doing 3 significant digits, right? 9.64% would be my mass of KCl. They did the exact same thing, mass percent equals mass of KCl to total mass times 100, which is good. And then they did the exact same math here. You get 9.63, 9.64. That's correct. Sweet. So let's look at B here. 2B. It says calculate the mole fraction of the ionic species. So we're talking about mole fraction of KCl in solution, right? In solution. So what do we mean by when we talk about mole fraction? So take a moment to think about this problem as well. What is a mole fraction? So if you look at the if you think about it in terms of what the word means, so we have mole. So we're working in moles, and then it's a fraction. So it's going to be a proportion or ratio of KCl in total solution. Right? So we're comparing moles of KCl and total moles, right? So that's what we're doing. So it's basically the same thing as mass percent, except what we're doing is we are, instead of using the mass, we're using the moles, right? So again, I can say that mole fraction would equal the moles of KCl divided by total moles, right? Total moles in solution, right? It would be a percent, so we would multiply that by 100%, right? Actually, no, it's not percent, sorry, it's just a fraction, so we don't actually have to multiply that by 100%, sorry. It's just a fraction here, right? And that's going to equal, so let's see, we have our moles of KCl. How do we solve for moles of KCl? We have to do moles equals mass over molar mass, right? So this would be mass of KCl divided by molar mass of KCl. This is all divided by total moles of solution, right? So this would be mass of KCl divided by molar mass of KCl plus, I need the mass of water, and I need divided by the molar mass of water, right? So again, this here is a big formula, but it's not really that confusing, right? And this here is, let me just in red. This here is NKCl, so the moles of potassium chloride. This here is also the moles of KCl, and this is the moles of H2O, right? So that's what all we're doing here. We're taking the moles of KCl and we're dividing it by the total moles in solution, right? So in solution means that it's going to be both the moles of potassium chloride and the water here. So that's what we're doing here. So let's plug this all into our calculator. Sorry, I did this in blue, right? So let's do that. Whoops. Siri randomly goes off. I don't know why. So this is massive potassium chloride. We have 24.0 divided by, what's the molar mass of potassium chloride? Well, we can look at our periodic table here. Right? Our potassium here is 39.09. So 39.0. I think it's 09 or 0. I'll say 0.10, 0.98. Let's take all the decimal. 0.98 plus our chloride, which is chlorine here, is 35.45, right? Plus 35.45 grams per mole. So that's going to be divided all by the same thing. So massive, so this is 24 again. 24.0 divided by 39.098 plus 35.45. And then I'm going to add that by the moles of water, right? The moles of water, I have the mass of water, which is 225 grams. I'm going to divide it by the molar mass of water. So if, again, H2O here is water, right? I know that oxygen here is 16 grams per mole, and 2 hydrogens means 2 times 1 grams per mole, right? As you can see here, hydrogen has a molar mass of 1, and oxygen has a molar mass of 16, right? So I have 16 plus 2 hydrogens, which is 2, is 18, right? So this would be 18 grams per mole. So now what we can do is we can plug this all into our calculator and get the mole fraction here. Let's calculate that. So we have 24 divided by 39.098 plus 38.45. Yeah, it's 38.45, right? Oh, 35.45. My writing is really bad. 35.45. This would give me a mole fraction of 0.319. Would be our numerator, 0.319. 3219, sorry. 3219. 3219. This would be moles now. And this would be, again, 0.3219 moles plus our moles of water, which is 225 divided by 18, which will give us 12.5 moles. And then this equation now becomes really nice, right? So again, I have here 0.3219 divided by, this is 0.3219 plus 12.5. I'm going to get a value of 12.8219. And then just have to divide the two numbers, right? 0.3219 divided by 12.8219 would give me a value of 0.0251 would be my mole fraction for this question here. So again, what I did here was, it kind of looks complicated, but it really isn't. Again, it's just the moles of potassium chloride divided by the total moles in solution, right? So I found the moles of potassium chloride. I don't know why. Tchaikovsky, nice. Moles of potassium chloride here divided by the moles of potassium chloride and moles of water, right? So this is the total moles in solution would be the denominator here, and the numerator here is the moles of potassium chloride, and then I just did it's basically just math, right? Again, I know what moles equals mass over molar mass, right? So mass over molar mass divided by mass over molar mass plus mass over molar mass, right? And then again, I know these two here are the same, right? These two here are potassium, moles of potassium chloride. So I know it's 0.329 here and 0.329 here. And to solve for the moles here, I have, again, it's just mass over molar mass. So grams, so mass of water divided by the molar mass of water to give us 12.5. And then simply divided the two numbers out to get 0.251. So that's kind of our mole that's our mole fraction for this question here. Let's see what they did here. And they did the same thing. Mole fraction equals moles of KCl over total moles. That's good. Mass over molar mass gives you 3.217. I got 39. Close enough here. And then water is 225. Yeah, that's good. It was 12.48. I got 12.5. And they divided by the total here to get 0.251. And that's the exact same thing, 0.251. Sweet. So that's B. This is a long question. And then 2C would be calculate the molarity of KCl, right? So it says here, calculate the molarity of KCl if total volume of solution is 239 milliliters, right? Okay, so that's what it's saying. Molarity of KCl if total volume of solution is 239 milliliters. So maybe take a moment to think about this, and then we will take it up together. So again, what is molarity in the first place? What is the what is molarity? And we know molarity here is by concentration, right? We learned about concentration in grade 11 chemistry here in the Ontario curriculum, right? So we know that C here, where concentration equals moles over volume, right? N over V, right? And this here again, this is concentration equals moles over volume, right? And moles are MOL, and here is in liters, right? To get capital M, right, as our molarity, right? So that's kind of our concentration here. So to calculate the molarity of KCl in the solution if the total volume of a solution is 239 milliliters, right? Well, what we can do is we already have the moles of KCl already. We solve for it here, right? We know moles of KCl is 0.329, right? So what I can do is I can just simply say that this here is 0.3219, and this is moles of KCl, and we're dividing it by the total volume of solution is 239 milliliters, right? So the total volume is 239 milliliters, but we have to convert milliliters into liters, right? 200, and I'll do some blue, so it's because it's side work here. So we want it to be the SI unit for concentration, or concentration is moles per liters, right? And we're given our volume in milliliters, so we have to convert this into liters, right? So in order for us to do that, we have to divide by 1,000, right? So again, I have 1 liter equals 1,000 milliliters, right? And these two are going to cancel out, which means I'm dividing, right? So 239 milliliters divided by 1,000 would give me 0.239 liters. So we plug into 0.239 liters in this case, and we get the molarity of potassium chloride, which is 0.329 divided by 0.239. 0.3219, sorry, divided by 0.239, you get a molarity of I'm doing this in 3 decimal places, or 3 significant digits, so 1.35 molarity is my final answer here. And let's check our work here. It says molarity is moles over solute over liters of solution. It should be here total solution, but I guess I'll forgive that. 0.321937, almost the same. 0.239 liters, good. 1.34, 1.35, awesome. So that was a C, which is great. And let's do D now. Almost done one problem. It's a long problem here. It's 2D. It's asking us the molality of KCl in the solution. So we talk about this concept of molality. What is the concept of molality? We know that molality, or this is a small m, but not to be confused with mass. So I'm just going to write it out. Molality equals, we have the moles, obviously, because the word mole is a molality here. I'll do that in blue. We know that the word mole is a molality, right? So that's fine. So you know it's the moles of KCl, because that's what I need, right? Moles of KCl divided by, I'll put this into black, divided by we have kilograms. This is in a different unit, kilograms, or the mass, kilograms of solvent, right? Or in this case, what our solvent here is water, right? So we have this here is kg of water here in this case. So in order for us to solve that, we actually have, again, we have all these components here already, right? We have our moles of KCl. We've already used that. This is 0.3219 KCl, mole KCl. And we're dividing it simply by the mass of our, or in kilograms of our solvent, right? So we have here, we have 225 grams of water, and we have to convert that to kilograms. So in order for us to do that, let me do that in red here as side work. So we have 225 grams, and we have to change that to, we have to change that to kilograms, right? So in order for us to do that, we have to divide by 1,000, right? So I would say this is 1 kilogram equals, there's 1,000 grams in a kilogram, right? So we're dividing by 1,000, which will give us 0.225 kg. So 0.225 kilograms of water, which will give us our final answer, and I'll write this in blue, which is 0.3219 divided by 0.3219 divided by 0.225. It will give us an answer of 1.43 will be our final answer for our molality of potassium chloride in solution. So 1.43 would be our molality for our solution here. And this is in moles per kilogram, right? Moles per kilogram here, 1.43 moles per kilogram. So again, same thing here. 0.3217 divided by 0.225, and again, you got 1.43 moles per kilogram, or m here, if you want to use the units here. And so this is here, great solution, perfect solution and analysis here. So that's awesome. So that was question 2, by the way. That's one question. So I don't know if I can finish all 10 problems today, because this was a 4-part question, but we'll try our best, and if not, we can save it for a later video, maybe on Thursday when I stream again. That's totally fine. So let's do number 3 now. So number 3 here is, how do you find the max mass of oxygen in the sample of 7.2 grams of this is aluminum sulfate? So it says here, mass of oxygen in 7.2 grams of Al2SO4 right? So how would you solve for the mass of oxygen? And when we talk about oxygen here, this mass of oxygen is this guy here, right? This oxygen here. So what do we have to do first is, again, we know our stoichiometry. We know our stoichiometry. We know moles equals mass over molar mass, right? So in order for us to do that, we have to find the mass of our oxygen. We have the mass of our oxygen here, which is 7.2 grams, or actually we have our mass of aluminum sulfate, right? 7.2 grams of aluminum sulfate. And what we're going to do is we're divide by the molar mass of our aluminum sulfate to get our moles, right? So for us to do that, we have to, let's solve for moles first, because that's kind of the default. What we want to do is we want to always solve for our moles first. So in order for us to calculate molar mass, I'm going to do this in blue. So what we have is we have 2 aluminum atoms here. So aluminum is 26.982. So we have 2 aluminums, 26.982 grams per mole, plus we have here SO4 we have 3 sulfur, right? Remember this 3 has to go into here and into here as well, kind of like distributive property. So 3 sulfurs, we have 32.06 plus, and then we have 4 times 3 here is 12 oxygens, right? So we have 12 times, I know the molar mass of oxygen is 16 here. So that's what we have to do for our molar mass, and then for moles, we're going to get a value of, I'm just going to plug this into my calculator. I have 7.2 grams of mass of aluminum sulfate, and then I'm going to have 2 times 26.982 plus 3 times 32.06 plus, 3 times 32.06 plus 12 times 16 here, right? Which will give me a molar mass of, this is 342.14. So that's what they did here, right? But they didn't really break it down into steps. So I don't really like, because I don't know where am I getting 54, where am I getting 96. This is a more concise step-by-step solution here. So this would be here. This is 7.2 grams over 342.14 grams per mole, right? That's fine. We can divide this out, and we can say 7.2 divided by 342.14 would give us 0.02 here. This is 0.021 moles of, this is aluminum sulfate. Sweet. So that's fine. So what we can do now is we have the moles and we have the molar mass. What we can do is we can do a proportion, right? So basically what that means is we look at our chemical formula here. It's Al2SO4, SO4 3, right? So we have here, so in total we have 2 aluminum atoms, we have 3 sulfur atoms, and we have 12 oxygen atoms, right? So all of these make up the aluminum sulfate, right? So we have 2, and we add this together. 2 plus 3 is 5, plus 12 is 17, right? We have 17 total atoms in our molecule here. So of the 17 atoms, 12 of them is our oxygen. We have 12 of them is our oxygen here. So what we can do is we can use this 12 as our kind of proportion here, and what we can do is we can multiply 12 to get our mass of our oxygen, right? So we have here again, we have 7.2 grams of aluminum sulfate. And what we can do is we are going to solve for our sorry. So we can solve for our moles, right? So we have here, which was 0.02 grams here. And what we can do is we can then multiply that by 12 here. 12, because this is our 12, we have 12 oxygen atoms. We can multiply, and then we can multiply the molar mass of that to get the molar mass of oxygen, which is 16, to get our solution here. So, so let me write this out here. So we have here, this is 7, sorry, hold up. We have, yeah. So we have 7.20, and this is actually what they did here. So I'm simply just rewriting their solution because their solution is correct. Of aluminum sulfate, 7.20 times, I can assume that there's 1 mole of SO4 minus, in this case, Al2SO4 3 divided by the molar mass, which is 342.14. And then we can multiply that by, we have 12 oxygens, right, per 1 mole. And then we can multiply this by 16 grams per mole, right? And that's what we're doing here, per 1 mole, right? And then we get, I'll plug this basically all into my calculator. We have 7.2 times, we have 1 divided by 342.14 times 12 times 16. I would get 4.04 grams of our solution here. Oh, sorry, of oxygen here, right? So we have these grams cancel out. The moles will also cancel out here. Actually, sorry, grams don't cancel out. Moles and moles cancel out here. And we have 12 oxygens here. This is 12 moles per mole. 12 moles. So these two cancel out. And one of my grams cancels out here. And my moles cancel out with this mole here. So I would get 4.04 grams per oxygen here. So this here is our correct answer, and that's what they got here as well. So I'm going to say here, great solution and analysis. So the solution is correct. Okay, so let me look at this question 4 now, right? So question 4 is a hasis law problem. So question 4 here says that consider these reactions where M represents a generic metal, and it gives you all these formulas, and you have to determine the enthalpy of the following reactions. So let me write this down. Let me write this down in blue. So it says here it's 2m plus, this is our target, plus 3Cl2 gas yields 2m Cl3 in solid. So we want the delta H, the enthalpy of this reaction, right? So this is a grade 12 problem actually. So I accidentally put a grade 12 problem here, but it's okay. We can look at this. For those in the U.S., you probably seen this before. So we have 4 chemical form equations we can look at. So this is 2m times S plus 6HCl aqueous yields 2mCl3 aqueous plus 3H2, and then the enthalpy of this reaction, I'm going to move this over, would be delta H would be negative 569 kilojoules. We have HCl is HCl gas, yields HCl aqueous, and then the delta H for this one is negative 74.8. We have H2 gas. Let me shift this over. We have H2 gas plus Cl2 gas yields, we have 2HCl gas, and the delta H for this is negative 1,455 kilojoules. And we have finally MCl3 solid would get, I have MCl3 aqueous, and this is delta H equals negative 405 kilojoules. Okay, so we have all of these things written out here for us. This here is in kilojoules, sorry, negative, whatever. Okay, so what we have to do in the hasis problem is we have to make this target. The blue one here is our target formula, and it's comprised of these secondary or these other chemical formulas. So let's look at I'll color coordinate this for you. So let's look at the first guy here. So this is, I need 2ms, right? So I have 2ms here in our left side, which is good. So they all have to be on the same side as well. So some sort of metal, generic metal. So 2ms, good. And then I need to have, so that's good. So I need to use this first equation here, 2ms, because that's good. Where can I find 3Cl2? I can find 3Cl2 in the reactant side with this formula here, right? But I only have 1 Cl2 here. I need 3, which means I have to multiply this entire equation by 3, which means I have to multiply the enthalpy also by 3. So let me multiply here by 3 first, and let me get the enthalpy here is negative 1,845 times 3, right? Which is negative 5,535 kilojoules. Okay, so we have that here. So now this here becomes this is 3 now. This here is 3, and this here is 6, right? And because I'm multiplying this entire equation by 3, so this is 6 now. And that's going to get me, so I can delete these brackets here. Here. And so I multiply by 3, right? And so which means my enthalpy multiplies by 3 as well. So that's good. I have 3Cl2 now. And then I need to make 2 MCl3 solid, right? 2 MCl3 solid. So I see that my MCl3 solid is on this side of the reactants. So I want it to be a product side, which means I have to flip these two guys. I have to flip my aqueous one to go on this side, and my solid to go on the product side. So in order for me to do that, I simply just flip the enthalpy sign here. So this here I'm going to multiply by -1, which is 405 kilojoules. So now what I can do is I can rewrite this equation here, and I can flip it to say that this is MCl. So this MCl3 AQ yields MCl3 solid. And I actually have 2 of them. I need 2 of them here, which means I have to multiply this entire equation by 2, right? So if I add a 2 here and a 2 here, then I would have to multiply this enthalpy here by 2, which would get me give me, let's see, this is 910 kilojoules. Okay, sweet. So I did that. So now I've accounted for all these things, but I have some side reactions I need to account for, right? I have two metal solids here. I'll do this in red. What do I need? I need so what I have so far in terms of my target is I'm gonna do the target stuff in red because that's what we need, right? I need this, and this, which I can get from two metal solids here. I have 3 Cl2 here, and I have 2 MCl3 solids, right? So this is the target equation I need, 1, 2, and 3, right? So let me label this 1, 2, and 3, 1, 2, and 3. Actually, the numbers might mess you up here, actually. I'm just gonna I'm not gonna write the numbers here. So, and what I also have is I have some side stuff, right? In order for me to use the first reaction here, I have to, I have some HCl being produced, and I also have some hydrogen gas and some other stuff here. So, what that does is, if I combine all of these equations together, what that means is that if I have a reactants onto the side, and if I make it in my products, it cancels out, right? So, for example, I've made here my reactants here for equation 4 was 2 MCl3s, right? And if I make 2 MCl3 in my equation here, this can also this reaction and this reaction here, because this is in the product side, this is the reactant side, is going to be used up in my general reaction. So what I can do is I can simply just cross these two out because it's being made and being produced. Same thing for my hydrogen gas. I believe I forgot to state here, but this H2 is in gas form, which means I have 3 H2 on the reactants and 3 H2 on the products. So these also cancel out, which is great because I don't need those in my general equation. I don't have my general equation here, right? The goal is to cross out all the things that are not my main products here, the side products here in this case. So all I'm left with is I have to deal with HCl AQ, HCl grams, and HCl AQ on this side, right? And as I can see here, I have an HCl gas on the side, but I have an HCl AQ on the side. And so I can't cross those two out, but I can cross out this grams here and this grams here only if I multiply this here by 6, right? So I need to multiply, I need to multiply this entire second equation by 6 in order for me to cancel it out. So let me multiply here by 6 and 6, which means that changes the enthalpy from negative 74.8. I'm going to multiply that entire thing by 6, which will get me negative 74.8 times 6 will give me negative 448.8 kilojoules. That's okay. And what that does is that allows me to cross out, I have hydrogen chloride gas and hydrogen chloride gas, so I can cross these two guys out as well. And then finally, I have here, I'm reacting hydrochloric acid and it's producing hydrochloric acid, right? I have 6 of these and 6 of these. So all I'm left here in the red is I have 2 MS, which is good, the main reaction, plus 3 chlorines, so 3 chlorine gases. It's going to make by 2 MCl3. Everything else is crossed out. So this is Hess law. So that's what we did there. So this is perfect in terms of our reactions balancing out. And what I'm left with all these enthalpies, right? I have all these changed enthalpies here. So for the first one here, the first reaction, I didn't do anything to this reaction here. So this here is still negative 569, right? Negative 569 kilojoules. What I'm going to say, I have to add up all the enthalpies here, right? So again, I'm going to erase this. This is simply just 910 kilojoules. So this is 910, 910 kilojoules, and I multiplied this by 2 here. So in the second equation, I multiplied everything by 6 here, right? Everything's here by 6, so I got negative 448, right? I have this enthalpy multiplied by 6, I would get this number here. The third equation, I multiplied everything by 3, right? Everything by 3 gave me, so I would multiply the entire enthalpy here by 3, I'd get this number here. And then lastly, what I did here was I flipped the equation so I have to multiply it by negative 1. So this here became, instead of negative 405, it became positive 405, and I also multiplied it by 2, right? So I can cancel out the 2 MCl3 in the aqueous form and the 2 MCl3 in the aqueous form here. So that's it's signified by this 2 here. So I can add all of these enthalpies up to get the enthalpy of my reaction for the first one, right? So let's add this up. So it's negative 569 plus negative 448.8 plus negative 5,535 plus negative, or this positive 910, which would finally give me an enthalpy of a reaction, which is negative 5,642.8 kilojoules. So this will be my delta H for the main reaction, which was this one over here. So let's look at our, so this here was our answer here. So let's look at our solution. So they, it's a very, very long solution like I did before. So they said they use Hess's law for enthalpy changes, 2m's to the left. So equation 1 remains the same. Good. We need to cancel out, let me look at this. We need to cancel out HCl. So we have to multiply the equation by 6, and that's what they did here. Then, so they would get this here. They add both equations to get this. We cancel out common terms, cancel HCl and H2. Equation 3 is multiplied by 3. That's great. And they added both equations. Again, they canceled the common terms. And now we need MCl3 in solid state, not aqueous. So we, equation 4, they inverted it, which is good. And they multiplied by 2, right? So that's what they did here. And then they added up all the enthalpies to get 5,742.8. I think they're off by 1 here. Or am I off by 1? I got 5,742. I have 5,642. So let's see. Are they off by 1, or did I copy something wrong here? Negative 569. That's good. Negative 774.8. 1,845 and negative 405. I believe I multiplied everything correctly here. Multiplied by 6, multiplied by 3, and then multiplied by negative 1 and 2, right? So I think their problem is actually off by 100. So let me just double check their math here. I'm gonna double check this guy here. So 6,552 plus 810 will give me negative 5,742. Oh, yes. So my math is wrong. Sorry. My math is wrong here. I see what I did wrong. It's this problem here. Negative 405 times negative 1 times 2 here would give me a value of 810, not 910, which means the answer here was correct. 810 kilojoules, which means this 5 becomes a 7 when I added it all up. So that here is our final equation. So I actually did my math wrong here. I did negative 4. I didn't use a calculator for this, so of course, silly me. 405 times 2 here is 810 here. Negative 405 times negative 1 times positive 2 is 810 kilojoules, which is the correct answer. So this here is a correct solution. Perfect solution and analysis. My bad for that. Sorry, guys. Sweet. Okay, so that was all number 4. So I'm going to number 5. About 15 minutes left. So hopefully I can answer as many problems as possible. This is question 5. So explain what the different ways to represent compounds. Why are there so many, right? So this is the concept of structural formulas. Structural or molecular compounds, or actually, I mean, it's in terms of there's actually 2 different ways to look at it. There's a ways of looking at in terms of a diagram and versus formula, right? So when we talk about diagram, it's more so for organic chemistry, right? For in diagrams, there are like 3 different ones, right? We have structural diagrams. We have a condensed structural, which is the same thing as structure, and we have line diagrams, right? So for example, a structural diagram of ethene would look something like this, right? Ethylene would look, we have a CH2, double bonded CH2, right? And for a line diagram, we would just get simply just that, right? So these are 2 ways to look at diagrams here, and we can also look at them as formulas, right? So as formulas, I'm going to do them in red, and we can look at, there's 2 different types of formulas, right? There's empirical formulas and there's molecular formulas, right? I misspelled molecular formulas, right? So for example, if I'm taking, this is ethylene as an example here. The empirical formula for ethylene would be, I'll just in red, would be just simply just adding, I'm adding all these compounds, right? All compounds. I have 2 carbons and 4 hydrogens here. So it'd be simply just C2H4, right? Would be my formula here. And in this case, the molecular formula is the same thing as my empirical. It's still C2H4, right? So, but if you recall, actually, so it's C2H4 would be my empirical and my molecular formula in this case here. And remember, what we can do with molecular formulas is if we have different compound here, it's simply just a ratio, right, for molecular formula. So if we had something like, we can multiply this here by 2, you get C4H8, right, which is a totally different compound. It's not ethylene anymore, but this would be the molecular formula, and this here would then be the empirical formula, right? So again, empirical formula, you could think of it as the lowest terms, but when we think about lowest terms, it doesn't change it always changes the integrity of the chemical formula, right? So there's a limit as to how you can express both of these things in terms of formula and in terms of diagrams. So again, the diagram is much more specific. It shows you bonding. It shows you how atoms are connected together. So diagram is actually much better than a formula here. C2H4 and C4H8. Again, there's isomers with this, right? Not with ethylene, but with this one here, with butylene or butene. There's structural isomers here, right? So again, here it doesn't account for those ones here. This could be connected in a cyclobutane form, and I wouldn't be able to figure that out with the molecular formula. So in this case, we have to use both of them for us to infer both the geometry, the atoms that are present, bonding, and all those things are needed for us to. So we need to have both the formula and the diagram for us to represent different compounds. So hopefully that answers question 5 here. When we use diagrams and formulas to represent geometry, type of bonding. Even atomic size, really. Size can be kind of represented. Electronegativity can be represented as well. And obviously, number of atoms in the formula here. So diagram has its perks, but the formula also has its perks as well. So that's great. So that's question 5 here. Let me look at the problem here. It says the chemical formulas and molecular models. So it's kind of the same thing. They broke it down to empirical and molecular formulas, which is great. Structural formulas and molecular formulas, space filling. They talk about bonding. You talk about molecular shape and orbitals as well. And they talked about how relative number of atoms and molecular formulas, actual number of atoms, which is great. So yeah, this is a good explanation. It's basically a summary of what I kind of said. So great summary, great solution and analysis here. Okay, we are now on number 6. So it says here, how many valence electrons are in an iron atom? So valence electrons of iron atom. So iron is actually a very unique element. When we talk about iron here exists in terms of what it is a multivalent compound, right? When we talk about multivalent, we talk about atoms that have different charges, right? What they can have is they can have different charges. So Fe is iron, right? Fe exists in 2 different states, you can say, or charges. Actually, not states. It's more so charges. So Fe can be 2+, or Fe can be in a 3+ electron configuration. So these are both charges of their multivalent metal compounds. So again, more commonly, so iron is multivalent, copper, and what else? Silver, and other kind of metals are all multivalent metal compounds. So when we talk about valence electrons, it's a bit harder for us to say what are the valence electrons of an iron atom, but we have to talk about something called electron configuration when we talk about a valence electron. So what we can do is we can actually draw out our electron configuration for iron. And for the sake of time, I'm not going to draw it out, actually, because I only have about 10 minutes left, and I really want to get through the other questions. So I'm going to see here what the solution is, and I'm going to see that for iron, it doesn't actually follow this one here. It follows something like this. The electron configuration of iron is this here. It has 26 electrons, right? So I'm going to verify that iron indeed has 26 electrons. So what they can do is they drew out the electron configuration of iron, right? So iron has 1s2, 2s2, 2p6, 3s2, 3p2, 3d6, and 4s2, right? So 4s2, let me just double check that. So 1s2 is 1, 2, that's good. 2s2 is these two. 2p6 is this block here. 3s2 is here. 3d6 is here, and 4s2 is here. 4s2 would make it here, right? And then it would be whatever 1, 2, 3, 4, 5, 6. It would be 4. It would be a 3 in the 3p block here. So that's what they did here. 3s2 and 3d6 is here, and then 3p2 would be 1 and 2. I think that's actually the electron configuration of titanium. I don't think that's the electron configuration here. 1s2, 2s2, 2p6, 3s2, 3d6, and then 4s2, and 3p2 would have titanium. Let me just do a quick Google search. I don't think this is electron configuration of iron. Let me electron configuration of iron. Oh, well, it really depends on the charge here, right? Because I don't know if it's Fe2 plus or 3 plus here. So if it's just iron, I'm going to say it's just simply Fe. Because I don't know what the charge here is, right, of Fe here. So, because I have this iron belongs here, and I don't know what charge it is, right? So I'm going to assume that it would have the same electron configuration as kind of this 4s2 here in this calcium here, because I don't know what the charge is. So that's what the electron configuration is, 4s2 here, right? This is the shortened form of the electron configuration. So they also drew an atom here. So therefore, they drew a distribution, right? So again, 1s2 has two electrons, 2s2 has 2, 2p6 has 6, 3s2 has 2, so on and so forth. And then you realize that the last block in the last valence electrons here, you have 3d, 6, and 4s2. So 6 plus 2 means it has iron has 8 valence electrons, right? You're adding these exponents here, right? Because 3d6, I have 6 electrons in that shell, and then 4s2 is I have 2 electrons in that shell as well. But again, they're all in the same energy level, right? They're all in that in the 4s2 block, which means it's because that's on the outside energy level. So I have 1, 2 here, and then 1, 2, 3, 4, 5, 6. All of these electrons here contribute to the valence electrons, because they all participate in bonding. When we talk about valence electrons, it's very, very hard, because what it does is it forces us to use a kind of a Bohr-Rutherford approach, which is Bohr-Rutherford model, which is technically incorrect, because we have to actually use the electron configuration model. So when we talk about valence electron, traditionally it's more so, it's just the electrons on the outer shell, right? But in this case, valence electrons states that it's the electrons that are needed for bonding, and all of these 8 electrons are responsible for bonding, and that's how we get these charges here, right? Fe2 plus and 3 plus is simply just the rearrangement of these valence electrons here. So this solution is correct. I like the solution in terms of what they did was they actually had the model here. But I would have liked if they included Fe2 plus and Fe3 plus, because that's what the charges that are usually present in an iron electron, right? So again, this valence electron, it can fluctuate depending on what the charge is. So I'm going to say here, solution is correct for a neutral Fe atom. However, would have liked to see solutions for Fe. This is 2 plus and Fe3 plus as well, because iron is a multivalent atom. So I'm going to say the solution is correct here. So that's good. That was number 6. All right, we have a couple minutes, 5 minutes left. These ones are actually a bit easier here. So number 7. So again, that was a little bit of grade 12 here, grade 12 chemistry. We're going to talk about electron configuration and hasis law. Both of those questions we took longer on because they're in grade 12. They're a grade 12 problem here. So it says here, what is the chemical formula for nitrogen? Again, very, very easy. Chemical formula is simply just like you can go into your periodic table and you can find out where nitrogen is. And if you know nitrogen is a gas, which means it probably is on the right side of the periodic table. And as you can see, nitrogen exists here, right? And it says nitrogen here, it has a atomic number 7. Atomic mass is 14.007. It's denoted by the element symbol of N, right? So in this case, chemical formula for nitrogen is N. Done. It's very, very easy, right? And this is probably a grade 9 type of science question when we look at how do we look at the periodic table, right? Remember, metals are usually on the left side and the gases are on the right side. So that's how we quickly analyze where we can find stuff on the periodic table. Nitrogen is obviously gas. It's in the air. So it's all probably on the right side. And as you can see, it's on number 7 here. So nitrogen is simply just denoted by N. Good. That was easy. Let's do number 8. So this here, they said here chemical formula technique introduced about chemical proportions. That's good. Nitrogen has a symbol of N. Nitrogen gas has chemical formula N2, right? So they asked for chemical formula for nitrogen, right? But nitrogen gas, as we know, is a diatomic molecule, right? So if you remember Hofbrinkel, or if I write down Hofbrinkel, so this is Hofbrinkel. And what this is, it's a mnemonic to help us memorize our diatomic molecule. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine all exist in pairs of 2. They don't exist by itself, just as by itself. So like Cl, it does not exist by itself. It's always Cl2 or H2 or F2 or Br2. So these are all diatomic molecules. But in this question, they asked for just simply nitrogen, so we can just say N. If they ask for nitrogen gas, we would always write N2 here. So this here is great solution, and analysis. Solution is correct. That's good. And let's look at number 8 here. It says, what is a neutral atom? So it's asking us to find what is a neutral atom. A neutral. So it says, what is a neutral atom? So when we talk about a neutral atom, we're talking about this idea of ions and cations, right? Ions are not neutral. Ions have a charge, right? We know that cations are positive. So cations have positive charge, whereas anions have a negative charge, right? So when we talk about neutral atom means that it has no charge, right? Neutral means no charge. So how do we get something that's no charge? We would have to do, we would need an element that has both the number of protons equals the number of electrons. So for example, let me use hydrogen as the example here. Hydrogen, we know from our hydrogen, I'm just simply one hydrogen atom, so H here, not hydrogen gas. H here has an atomic symbol of 1. So I know it has 1 proton, which means it also has 1 electron, right? So hydrogen contains 1 proton and 1 electron, which means that this atom here is neutral, right? It's neutral. There's no charge on this one right here, right? But ideally, usually what would happen is that H here would either gain an electron or lose an electron to be more stable, right? So you can sometimes get H plus, or where I have one of the electrons being lost here, or I could get something like H minus, where the electrons being I added an electron to the shell, right? Usually it's H plus here, but it's not usually the case. That's not for every case here. So it says here a neutral atom has an equal number of protons and electrons, or an equal number of positive and negative charge. Good, that's basically it. It just has neutral means no charge, which means it has the equal amount of, so let me write here, equal amount of so number of protons equals number of electrons, and that's all it is for a neutral atom. Good. Good solution and analysis. That's great. Solution's correct. And let's see if let me do one more problem here. I think I'll be question 9, so I might not be able to get through 10 questions today. I can do this in 1 minute. What is the formula for magnesium nitride? So magnesium nitride. So all we have to do is we have to look at our periodic table and figure out where's magnesium. Magnesium is a metal, which means it exists on my left side here. I see Mg, so that's my magnesium, right? Mg here. So Mg is my magnesium. And what's my charge of magnesium? Charge here, if it's in the second group, it has a +2 charge, right? So 2 plus magnesium. Nitride is simply just a short form of nitrogen, right? So I have nitrogen here, again, non-metals here, non-metals or gases are here, which means N would be on my right side. So N here is, it's a group, lies on group 15. So I have N here, and what's the charge of nitrogen in this case? Nitrogen has a charge of 3 minus, right? Because again, neon has a charge of, it's full octets, so it's 8. I have 1 minus here, 2 minus, and 3 minus, right, for nitrogen. So this is a 3 minus charge. So what we can do, we can either do the crisscross method, if you might learn that before. So I'll show you the crisscross method, which means you just cross the charges and you get the answer. So magnesium would then get this charge, not get this charge, but magnesium would be then would have a subscript of 3, and nitrogen would have a subscript of 2, and this would be your answer, right? Mg3 and 2 is our answer. So you can do the crisscross method, or what you can do is you can simply just ask yourself what's the greatest common factor between 2 and 3? The answer here is 6, which means I have to multiply. I need 3 magnesiums to get this, and I need 2 nitrogens to get this charge of 6, right? Because then I'll have 6 plus. I'll have 6 plus here, so I have 3 Mg 6 plus, and then I'll have N2 would have 6 minus, right? 3 times 2 here is 6. These charges was cancel out to get. Sorry, this is not 3 here. This here would be 3. And then these charges cancel out to get Mg3 and 2. So either way you look at it, you get Mg3 and 2, which would probably be the answer. Mg3 and 2 is our answer. So they simply just do the neutral method here. The crisscross method. So there's 2 ways to look at it. But this here is a good solution. They did other ones here. Good solution and analysis. So that here is going to end my video. I only did 9 questions today, unfortunately, because the hasis law problem did take too long. But so again, if you're watching from home, thank you for watching. I'm going to be back in about an hour, and I'm going to do actually some very do more difficult problems, and probably what you've seen like first year university level organic chemistry and second year level organic chemistry. So stay tuned for that if you're interested. I'm going to probably stream about 2 p.m. Eastern, so stay tuned for that. But if not, again, thank you for watching. You can check out our YouTube videos on OneClass to review any of these solutions that we've gone together. And yeah, again, thank you for watching, and have a great day. Stay safe, everybody.